This is problem number 1 on the practice problems for test number 1. The graph below is that of f of x, which gives the rate of change of the amount of water in a reservoir measured in thousands of gallons of water a day as a function of x, the number of days that have passed. So I've got a graph here, we'll analyze it, but let's first look at the first question. Part A, when is there the most water in the reservoir? Okay, so now let's see if we can really understand what this graph is telling us. So this graph right here is a rate of change. That's a key phrase for us. It represents the rate at which the amount of water in the reservoir is changing. And so let's take a look at a few points on this graph. For example, this point right here says that if we are 10, what are the time units here? Days. 10 days into this experiment, then the rate at which the water level is changing is about negative 0.5, and what's the unit there? Thousands of gallons of water a day. So 0.5 thousands, I guess that's really just 500. So what that means is that 10 days into this experiment, or at that one moment in time, the rate of change of the amount of water in the reservoir is decreasing at about 500 gallons of water per day. And so actually all of these numbers here represent times when the water level is decreasing. You can think of this graph very clearly as a derivative of something. I know we called it f, but we could just as well think of it as a derivative. And so whenever the derivative is negative, which it is all down here, then we know the original function is increasing. And then something changes because here we've got all these positive numbers up to the top, and then even as it continues to come back down, these are still positive numbers. So until we get to that spot right there, the rate of change of the amount of water in the reservoir is actually increasing. So we're gaining water for that whole purple time period. I guess I'll highlight it down here. And then we'll go back into the red for the rest of this because here, I won't go all the way to the axis, but these are all negative numbers. Even as we get past the bottom and start to go back up, still having negative numbers. So everything in the red represents places where the water in the tank is decreasing. The amount of water in the tank is decreasing. And that purple hump in the middle represents moments where the water level is increasing. And I think that's the key to understanding how to do maybe just about every part of this problem. So the first question says, when is there the most water in the reservoir? Okay, I don't know how much water I start with. It largely doesn't matter. But from whatever the starting point is, until we get to day, say, 60, what's happening to the amount of water in the reservoir? Well, it's decreasing that entire time. And then from day 60 to about 250, that's the purple, we're gaining water the entire time, and then we lose water towards the end of this experiment after day 250. But the question is, can we figure out the comparison between how much water we actually lose in here compared to how much water we gain in here, and then maybe compared to how much water we lose here? And we can, because we know that if we think of this thing here as a derivative, and I'm going to go ahead and clean this up just so that we can draw other stuff on it. But if we think of this graph as a derivative, then we know that the area under a rate of change is the total change. So actually, the area of this red space in here represents how much water, the actual change in the amount of water in the reservoir happens over the course of those first 60 days. So I don't know what that area is. One of the parts of this problem is going to ask me to estimate, but really this question is about areas. So the purple area is how much water we gain from day 60 to 250, and then again we lose some area, we lose some water over there. So again, part A says, when is there the most water in the reservoir? Okay, I don't want to do any calculations just yet, but I can tell you that the amount that we lose here is not as much as the amount that we gain over here. Definitely that purple area is more. So when all is said and done, going from day 0 out here to day 250, when do we have more water in the tank? Well, in the first 60 days, what's happening to the amount of water is decreasing. We're losing some water, but then we more than make up for the amount that we lose because that purple area is much bigger than the red area. So on day 250, we definitely have more water than we did at the start on day 0. And then what happens after day 250? Well, we're back in the red. We're losing water again. So when is the, and that happens forever, at least as far as this graph is concerned. At the end of 1 year in this graph, it's still down here in the red. So I guess that means that we have the most water at the moment we change from positive rates of change to negatives. So at day 250 is when we have the most water in the tank. Part B, can you tell how much water is there at that time? Well, we can estimate the areas. We can estimate the red area, I think we will in just a minute, and we can estimate the purple area, and we can combine those to figure out how much water, how much the water changed, how many thousands of gallons of water change did we have in the reservoir. But there's a piece of information that's missing without which we cannot tell exactly how much water is there at that time. And the piece that's missing is how much water there is at the start of the experiment. So again, if we calculate the red area or estimate it and then do the same for purple, we can combine those two numbers and figure out by how much the water changed. How many thousands of gallons of water did we gain going from day 0 to day 250? And we would need to add that to the amount of water that we start with. So we don't have enough information. We'll write a tiny bit more than that. We can calculate areas to get the total change in the amount of water. But we don't know how much water we started with. Okay, moving on to part C. By how much does the water level change over the first 50 days? Maybe the word level there isn't, I don't want it to be misleading. It doesn't, we don't know anything about the shape of this tank. It's really just asking how much water did we lose in the first 50 days? How many thousands of gallons? So we've talked about the area problem. Here we're just going to estimate. So let's erase this piece here. We're going from day 0 to day 50. So it's really from here over to there, and then up and back. So that shape right there is what we're asked for to estimate the area of that thing. It is roughly trapezoidal, so I'm just going to use my trapezoid area formula. If you don't happen to know the trapezoid area formula, feel free to cut the trapezoid into a rectangle and a triangle. But I'm fancy, so I'll use my trapezoid formula. And the trapezoid formula says that the area is equal to half the height times the sum of the bases. Okay, the bases are the parallel sides. So in this case, the parallel sides of the trapezoid are the vertical sides, those two right there. So we're going to estimate how long they are. I'm going to call this a negative 0.8 at the bottom. And then where I drew that purple line, we'll call it about negative 0.2. Of course, for any estimation problem like this, there's a range of acceptable answers that will get you full credit on a test or quiz. So let's start plugging stuff in. So continuing with our formula, 1/2 of the height. Okay, I didn't write that yet, but the sum of the bases, negative 0.2, and then plus negative 0.8. And then the height is the line that's perpendicular to those parallel lines. So that's the horizontal line. We'll put it here in green, this distance right here. Okay, that's 50, that's given in the problem. So this is a 50, and you might be wondering why I'm including negatives there. Technically, it's an area, so those should all be positives because they're lengths. The negative will just kind of confirm that we've actually lost water. So 1/2 of 50 is 25, and then here in the parentheses is a negative 1, so negative 25, which means we lost, the reservoir lost 25,000 gallons of water. Again, it's okay if you don't have exactly that answer. Anything nearby will do fine. Part D. How does the amount of water at day 300 compare to the amount of water at day 0? Okay. So in this case, we're going up to 300. So we're going to get rid of that, and we're going to cut it off right here at 300. So the question is, how does the area in red there, plus the area in red that we found before, plus this little triangle piece there, how does that compare to the purple? Because the purple is when we're gaining water. The combined two red areas is when we're losing water. Again, we're not really looking to do any serious calculations. To my eye, it looks like the purple is bigger than the sum of the two reds. So that'll be my answer. and we'll write it here. Okay, part E, draw a possible sketch of the integral from a to x of f of x dx. Your sketch should be accurate enough to reveal maximums and minimums and inflection points in their correct locations. However, don't worry too much about getting the exact y values of your graph. Okay, first question you might have when looking at this is, what the heck is a? All right, a can be anything you want. The important thing here is that we know that anytime we're integrating from some number up to x, we're really just doing an area accumulation thing. So the question here is just asking you to sketch an area accumulation graph. So I'm going to choose to pick my a equal to 0. But it really doesn't make any difference what you choose. By choosing a equals 0, I'm saying let's start the experiment at time t equals 0 in terms of our graph. So we'll come down here, a very rough sketch of our graph. So I'll go by 50s. Okay, we're not worried about y values, so I won't even bother labeling the vertical axis with numbers, but I will say that the vertical axis is going to be an amount of water, amount of change of water, and that's going to be in thousands of gallons. Okay, so if I start my graph with a equals 0, then starting here, trying to figure out, is my first point here or here or here or here? Well, if x is also 0, then the integral from 0 to 0 is 0. So my graph is actually going to start at the origin, but your graph may start somewhere different. Totally fine. Okay, so we'll get rid of some of these. So we start at 0. Then what did we decide happened? Well, we knew that in the first 50 days, we calculated in part C that we lost about 25,000 gallons of water. So how do we indicate that here in the graph? Well, after 50 days, we are down 25,000 gallons of water. So I'll just put a dot right there. Again, I said I wasn't going to label. I'm going to erase that in just a second. But, you can plot a point. You got information from up above. Okay, so we have our dot there. Is that the bottom point on the graph? Because remember, around day 60 is when we start to actually get back into the purple and we gain water. So from 50, we actually lose water for another 10 days, and then we start to gain. So let's go back down here, and going between days 50 and 60, I actually lose a tiny bit more. But I know that at day 60, I'm at my bottom, because then we're about to enter the purple. And in the purple, we start to gain. And we haven't done any estimating for the area of the purple, and we're not going to. But at some point, the purple area, say from like here, maybe to here, at some point that purple area is perfectly going to cancel out the red area. The blue triangle I've just drawn may be past that point. But at some point, maybe around day 130 or so, those two areas are equal. And what's going to be true at the moment in time when the two areas are equal, what will the total change in water have been? It'll be 0. We'll be exactly right back to where we started. So maybe right around day 130 is when we have exactly canceled the water loss from the first 60 days with the water gain for the next however many days. But then the purple keeps going. Purple definitely dominates the first red area. So we just keep gaining, gaining, gaining until we get to day 250 right there. So let's start increasing. We'll be positive and going up until we get to day 250. Actually, I think I want to make this not quite as steep here. Okay, so maybe we get to there, and then we increase, increase, increase until we get to day 250. So day 250 is the moment in time where we start to decrease again. And it's going to start decreasing because from day 250 onwards, we're back in the red. And so we're losing, losing, losing all the way in the red. And so I don't know exactly when it's going to hit the axis. It maybe gets there, maybe it doesn't get there. It's not really clear. Doesn't much matter. You just have to show me you know that it's decreasing. And I did talk a tiny bit about inflection points in this problem. So the last thing here is to just mention them again. So where do we have inflection points? Well, let's see. We know that somehow the number 150 is special on this graph, and that it's the highest point on this derivative graph that I'm looking at. So let's see what's going on at 150 in our rough sketch. We didn't really pay attention to 150 when we were graphing this thing. At least I didn't. Maybe you did. But 150 is here. Could that 150 be anything special? Well, goodness, it looks like maybe that's right around the inflection point. Can we confirm that using the calculus? Well, if you're looking for an inflection point, what are you really trying to do calculus-wise? Well, if I think of this as a derivative, I'm going to call it g prime instead of calling it the f that it's been the whole time. If I think of that as a g prime, then the graph that we were just doing at the bottom is g. It's like the area accumulation. It's an antiderivative. And so if we're looking for inflection points of the original g, that's the graph at the bottom of the screen here, then we're looking for places where g prime is equal to 0. So the question is, how do you get from g prime to g double prime? I think I might have said g prime a moment ago, and I meant g double prime. G double prime equals 0 is what we need. So how do you get from g prime to g double prime? Well, you take one derivative. To get from g prime to g double prime, you take one derivative. And so what we're saying here is that the graph of this guy, if you go one derivative up, we want it to equal 0. So if the graph of some function has one derivative up being 0, then what must be true? Well, the function must be flat at that point. And lo and behold, right there is the place where the function is flat. The derivative of the graph that I'm looking at right now is 0 at about 150 because the graph is flat there. And so that's the point that's one derivative up from g prime. And because that makes it g double prime, that's our inflection point. It's really quite tricky to kind of play these translation games, I think, with looking at derivatives and second derivatives and antiderivatives. But roughly 150, that max, is where we should have the point of inflection. And goodness, well, I feel like that must mean a little bit more then. Is there another point of inflection on this graph? The maximum was a point of inflection. We just saw the 150. Is there another maximum on the graph we're looking at now? No, but there is something else. There's a minimum right over there. There's a place where the graph is flat. So maybe around day 340 or so, we're going to have another inflection point down here. So what's going on at day 340? Well, I kind of petered my graph out at that point. But I guess what we're saying is that if it's been concave down this whole time here, maybe around day 340 is where it starts to change to concave up. So this point right here, roughly 340 is around the point of inflection. 150 is the other. Okay, last thing to say about this, and we're done, is that I started with a equals 0. I wrote it in green, which just meant that my graph started at the origin. But perfectly well, you could have started your graph somewhere else. You could start your graph up here, for example, choosing a different value of a. Wherever you start your graph, the graph is going to look like the blue. It's just going to start somewhere different. So if your graph started up there for some reason, then it would have come down, and it would have gone up, and it would just be a vertical translation of the graph that's in blue. And perfectly well, you could have started there and gone off the screen and then come up and then come down. Anything like any of those graphs are fine. And in fact, the answer in the answer key at the back of this list of sample problems doesn't look like my blue one. It's a vertical shift of my blue one.